Hey everyone, and welcome. Today, we're going to dive into the really cool world of graph transformations. We're going to break down how you can take one simple function and start to twist it, turn it, stretch it, and shift it into something totally new. Let's get right into it.
So have you ever wondered how it's possible that a single basic equation for a curve can be the starting point for literally endless other shapes? Well, it's not magic, I promise. It's all about a set of really simple, predictable rules. Think of it like you're being handed a toolkit for building any graph you can possibly imagine.
So, here's our game plan. We're going to start with the single most important concept, the difference between making a change inside a function versus outside. Then we'll get into shifting, stretching, and flipping graphs. And to top it all off, we'll put everything together to build a complex graph one step at a time.
Okay, let's get right to the heart of this. Seriously, if you can wrap your head around this one core idea, everything else we talk about today will just click into place. It all comes down to where you make the change to the function. Okay, this right here, this is the golden rule. If you change something inside the function's parentheses, right there next to the x, you're changing the graph horizontally, left and right. But if you change something outside of the function, you're affecting the graph vertically, so up and down. Just burn that into your brain. Inside is horizontal, outside is vertical. All right, let's kick things off with the easiest moves in our toolkit, just sliding the entire graph around the page without actually changing its shape. This is what we call translation. So, first up, vertical shifts. This is an outside change, right? It's happening outside the f of x. So it's going to affect the y-axis, just like our rule predicted. Add a number, the graph moves up. Subtract a number, it moves down. It really is that straightforward. And this graph shows it perfectly. That dotted line is our original sine wave. When we graph y equals sine of x plus 2, the whole thing just lifts up 2 spots. When we do sine of x minus 1.5, it drops down by 1.5. See, the shape is totally identical. It's just in a different place vertically. Now for the horizontal shifts. This is an inside change happening right next to the x. But here's the crucial part, and honestly, it's a little weird. Subtracting a number actually moves the graph to the right, and adding a number moves it to the left. For anything horizontal, you kind of have to think the opposite of your first instinct. And look, you can see the proof right here. Compared to our standard sine wave, sine of x plus 1 has shifted the whole graph 1 unit to the left, and sine of x minus 2.5 has pushed it 2.5 units to the right. It feels backward, I know, but it's a rock-solid rule. Okay, so we've got sliding the graph around down pat. Now let's get a little more creative and start changing its actual shape by stretching and squeezing it. Let's start vertically. When you multiply the entire function by some number, that's an outside change, remember? You either stretch it or you squeeze it vertically. If that number is bigger than 1, the graph gets taller, like you're pulling it. If it's a fraction between 0 and 1, it gets squashed down. And this slide shows that effect so clearly. The graph of 2 times sine of x is twice as tall as the original. Its peaks and valleys are way higher and lower. But then when you multiply by a half, like with sine of x over 2, you can see how it just flattens the wave out, squeezing it vertically. And yep, you guessed it, the horizontal version is an inside change, and it follows that same backward, counterintuitive logic. When you multiply the x inside the function, a number bigger than 1 actually squeezes the graph horizontally. It squishes it together, and a fraction between 0 and 1 will stretch it out. Again, just think opposite for horizontal. This graph just nails it. See how y equals sine of 2x completes a full cycle twice as fast? It's been squeezed horizontally. And y equals sine of x over 2 is all stretched out, taking twice as long to complete one wave. All right, we've shifted our graph, we've stretched it, now it's time to flip it. Reflections are another really powerful tool we can use, letting us create perfect mirror images across the axes. And you know what? The rules for flipping follow our core idea to a T. If you stick a negative sign outside the function affecting the whole thing, you flip the graph vertically, right over the x-axis. If you put that negative sign inside with the x, it flips the graph horizontally, over the y-axis. Okay, now let's look at a special case that can sometimes trip people up, the absolute value, or modulus. This can be tricky because where you put those absolute value bars completely changes what happens. Are they outside the function affecting the final y value, or inside affecting the x value before it even gets processed? Let's break it down. First, let's put the absolute value on the outside. Y equals the absolute value of f of x. What this does is it takes any part of the graph that's below the x-axis, anywhere y is negative, and it just flips it up to be positive. It's like the x-axis is a trampoline. You can see with the sine wave, all those dips just become bounces. But check this out. When we put the absolute value on the inside, y equals f of the absolute value of x, it is a completely different story. The function basically erases whatever the graph was doing on the left side for negative x values. Instead, it takes the entire right half of the graph and reflects it over to the left side, creating this perfectly symmetrical shape around the y-axis. All right, this is it, the grand finale. We've learned all the individual pieces of the puzzle. Shifting, stretching, flipping. Now we're going to combine all of them to build a pretty complex-looking graph from a very, very simple starting point. Let's try to build this beast. Y equals the absolute value of x minus 2 minus 3. The key is to always work from the inside out. So, step 1, we start with the absolute core, which is just y equals the absolute value of x. That's our basic V shape. Step 2, we deal with that minus 2. It's an outside change, so it just shifts the whole V down 2 units. Easy. Step 3. We apply the next set of absolute value bars. This is our bouncing rule, right? So the part of the graph that dipped below the axes gets flipped up, creating this cool W shape. And finally, step 4. That minus 3 on the very outside is another vertical shift, which moves our W down 3 units to its final spot. See? We just applied our simple rules, one after the other. So, by mastering just these few fundamental rules, you've basically been given a powerful toolkit. You can look at a really complicated equation and break it down into simple steps, or you could even start with a shape you want and try to build the function for it. The core idea is simple. What happens inside the parentheses changes the graph left and right. What happens outside changes it up and down. With that in mind, the only question left is, what graphs will you create?